Okay, so now we will continue our discussion with the Rayleigh-Plateau instability and the Navier-Stokes equation. So in our last lecture, we found out this complicated looking equation with the relationship of small r squared, the second derivative of r, and small r times the first derivative of r, and a relationship between 1 plus kr squared times large R equals 0. And if you are familiar with differential equations, you might notice that this takes on the form of a Bessel's equation, or more specifically, a modified Bessel's equation. So this is our Bessel's equation here, x and y, and you see the n squares and x squares and y, and you might think, hey, this looks kind of similar. But the most important question here is, what is the solution of this Bessel's equation? Well, the solution is even more complicated than the Bessel's equation, to be honest. But if you look at it, we call like this: y equals constant times jn minus ix and a2 times yn minus ix. It kind of looks all complicated, but this is what we call the Bessel function of the first kind, which is written by I and x, and the Bessel function of the second kind, which is written by k and x. And what is important here is that I and x, this component here, the first component or the Bessel function of the first kind, is exponentially growing, and the second component, the Bessel function of the second kind, is exponentially decaying. So in our case of the Rayleigh-Plateau instability, we will be considering only the first function here, the Bessel function of the first kind, because we only have to consider the component that is growing exponentially due to the perturbations. And if you look at it mathematically, we can also note that if we will be plugging kr into x, so the large k1 or the Bessel function of the second kind, if you plug in kr to x, it will go to infinity if you take r to 0. So if x or r here goes to 0, this function is going to go to infinite. So we don't have to consider the second term here. It's going to be much simpler. So we can write down these Bessel functions of the first kind like this, and the second kind like this. Okay, it's missing a kind of here. Okay, so but we don't have to consider this complicated Bessel function of the second kind, but only this Bessel function of the first kind. And what is also important to note is that, well, you have something called this kind of relationship. I0 is related to I1, but I'm missing another derivative here. So the derivative of I0, or the Bessel function of the first kind, is actually the Bessel function of the first kind plugging in n equals 1. The 0 and 1 here, you see, this is the n, you see, and where n comes from is actually from this first equation here, the modified Bessel's equation. In our equation, we see that, well, n, if we take k r as x, n will be 1 in our equation. But it's just useful to note that when n is 0, the derivative of I0 is going to be I1, which will be useful in our further discussions. Okay, so let's look at how this is actually related to solving our equation we earned from the momentum equations. Okay, firstly, what we want to do first is that we took this equation. Okay, this is our Bessel function, our modified Bessel's equation. We got this, and what we are going to do here is this. We took x is kr, y is r, and n equals 1. Therefore, we can simply say that r is c, when c is a constant, c times the Bessel function of the first kind, plugging in kr into x. That was simple. And secondly, what can we do? We can take the r equation, the r component of our Navier-Stokes equation, which was omega r equals minus 1 over rho times dp dr. And what we get from this relationship is intrinsically that dp dr is minus omega rho r, right? So this is going to be minus omega rho times r, where r is c times I1 and inside x we put kr. Okay, and this becomes minus omega rho times c times I0 prime kr because of this relationship we just defined here, right? We defined that I1, a function of I1 is going to be derivative of I0. So this is simply for mathematics. We see that there is a derivative here, right? There is a derivative here. So we want to kind of match it. It's like not a derivative. This guy's not a derivative of anybody, but this is a derivative, right? So you can imagine that it's just a mathematical technique, but if you want to match derivatives together, it's going to be easier to, you know, work them out mathematically. Okay, so what was the result we got from this? What is the result we can get from this? Well, it is that if we integrate this, since they are both derivatives, if we multiply both sides by dr and integrate it, we get dp integration is minus omega rho c I0 prime kr dr. Okay, we can easily integrate this and say that p, which is a function of r, is minus omega rho c over k times I0 kr. Okay, hey, it's like it used to be a derivative of the Bessel function, but it's now just I0. That's simple now. And you see that the k might like 1 over k comes out because we're taking this dr here, and kr is inside here, so it's like if you say that this is x, well, like dx becomes dr, that kind of stuff. Okay, you get pr as a function of r, and if you further simplify this, we get this equation here. We, in the beginning of our analysis, in the first part of our discussion, we said that P is actually PR times exponential omega T plus IKZ. So the total pressure, it's not just PR, not just a function of R, but we also have to consider the last part, which is the exponential part. So if we get total pressure, it's gonna be a function of omega K and R, which can be expressed as minus omega rho c over k times I0 kr exponential omega t plus ikz. Okay, and we have to apply our boundary conditions here. Okay, so what are our boundary conditions? We have two boundary conditions. Firstly, we have a kinematic condition on free surface, and secondly, we have what we call a normal stress balance on free surface. But we'll first look at the kinematic condition on our free surface, which is gonna be valid for when r is r0, right? Our r is r0 when it's a free surface. Firstly, we are going to equate the speed of our perturbed column with our fluid velocity. Because of our kinematic condition, it has to have the same speed. Well, or speed would be more sufficient instead of fluid velocity, but anyway, like, what we were talking about, the speed of the perturbed column and the speed of the fluid. Okay, the speed of the perturbed column, how can we express it? We can express it as the derivative of r with respect to time. And what is the fluid velocity? Well, we just learned in our last lecture that our fluid velocity or fluid speed is going to be simply UR, little UR. And this R, just so if you don't remember, this R can be expressed as the initial R0 plus this tiny perturbation times exponential omega t plus ikz. And you have to remember that UR, our fluid velocity, is a function of large r, which is a function of small r, large r times this exponential term. And large r is also another function which we just derived in our previous analysis. We just said here that Bessel equation modified Bessel's equation, we took the solution of it. We said that we are only gonna take care of the exponential growing term, which is the first Bessel function of the first kind. And here we said right? We said that r is a function of r. I mean, a large r is a function of small r, to be precise. And we have this constant here and the Bessel function of the first kind. Okay, that was our r, so we just write here, okay. R is a function of r is c times ri with a kr inside. So if we, and also another important fact here is that if we plug in this r inside this ur, we're gonna get our final expression for ur, which is this guy. Okay, it's simple now. We just have to do what they are telling us to do. And what this equation is telling us to do is to take the derivative of r with respect to time. Okay, let's take our derivative here. Okay, we took it and it's this. Great. It says epsilon omega times the exponential term, which is equivalent to this this originated from our ur. Okay, we can equate these two guys. So this guy just came from here, and they pop up like this, and we are gonna equate these two guys. And what does this equation tell us? Well, it will conclude that c, we can now determine what c is, our constant is. Our constant is epsilon omega over our I1 kr0. By the way, I just said that we are taking a free surface condition where r is our large r0. That's why we just plugged in r0 inside this r here. Okay? Okay, now that we know our c, everything is gonna be much easier, right? Yeah, because the c is gonna constantly come out again and again as we do our analysis. And secondly, our second equation, our normal stress balance on free surface. This is our second boundary condition. What was our first boundary condition? Our first boundary condition was a kinematic condition. Second condition is normal stress balance condition. And what is our normal stress balance condition? It is this, what we are quite familiar with. It's kind of related to the Young-Laplace equation, if you remember. P0 plus P is this guy, this surface tension plus 1 over R1 plus 1 over R2. In our cylinder case, we said that R2 is going to go to 0, right? I mean R2 is going to go to infinity if it's a cylinder, so the second term is going to go to 0, but if there is a perturbation, you will see later that it is no longer a perfect cylinder, so you have to consider both R1 and R2 terms. We will look at a picture later. And anyway, the Young-Laplace equation tells us simply that our P0 guy, which is for our cylinder or our mean pressure, is simply this. It doesn't have two terms, right? It's just defined by R0 and the surface tension, the gamma, right? What we want to know here, however, is not P0, it's P. So we can rewrite P as a function of, well, R1 and R2 and P0, right? So if we do a minus P0 to the left hand side and the right hand side, we get P equals minus P0 plus gamma times 1 over R1 plus 1 over R2, which can be expressed in terms of brackets because P0 is gamma over R0. So it's gamma times minus 1 over R0 plus 1 over R1 plus 1 over R2. Wow, that's simple. And we got our P, and as I told you, well, in the cylinder case, we did not have to consider the second part of the radius of curvature. We only had to consider the radial part, not the tangential part, because it was infinite. The second term was infinite. So it went to 0. The second term went to 0. But if it's not a perfect cylinder, it's going to have a radius of curvature along the both tangential and radial directions, so we have to consider both R1 and R2 like in this picture. Okay, so what is this going to tell us? Well, we just have to calculate, since we know R0, well, R0 is determined, we only have to consider R1 and R2, but the question here, is that how on earth are we gonna calculate R1 and R2, right? Well, okay, let's do this together. Okay, so this is gonna involve our calculations of radius of curvature, right? Okay, before we calculate our radius of curvature, why am I constantly missing something today? Okay, so we have our R equation like this written down here in the yellow box. R is R0 plus this perturbation term times the exponential term, if you remember correctly. So we are going to use this R again in order to derive our R1 and R2, or rather 1 over R1 and 1 over R2. So our radial component of our radius of curvature, by the way, this picture does not show like the uh, this picture doesn't really depict what's actually going on here, but it's just from our previous discussions about how radius of curvature can generally be expressed in terms of R1 and R2. But you have to remember that 1 over R1 here is for radial direction and 1 over R2 here is for tangential direction. So anyway, we are gonna take R1, and 1 over R1 is simply 1 over this R squiggly guy. That's just like this R guy just goes into R1, okay? So that's how we get 1 over R1. That's simple enough. We get 1 over R0 plus epsilon and the exponential term. But if you remember, we know that this R0 is much larger than the perturbations, or rather the perturbations are so minor, so small, that they are really ignorable, though not completely ignorable. So R0 is much larger than epsilon. We have this equation here with something in the denominator where one guy is large and one guy is small. In this case, we take some kind of mathematical trick. We know that 1 over 1 plus x is 1 minus x, when x is much smaller than 1, right? This was from mathematics. And we can see a similar structure here, so hey, why don't we just like change this R0 into 1 by dividing both sides by R0, and we'll end up with the same equation. So let's do that. We get 1 over R0 times this guy, which is basically like dividing the denominator by R0. And okay, we don't have to consider the 1 over R0 term anymore. And we get, so this guy here is our new x. Okay, so this guy is also much smaller than 1 because R0 is much larger than the perturbations. So this is gonna be not equivalent but quite similar to 1 over R0 times 1 minus epsilon over R0 and the exponential term. If you further simplify this, we get 1 over R0 minus epsilon over R squared times the exponential term. Okay, that was our first term for the radius of curvature, but what about our second term, 1 over R2? Well, it's a little more complicated in terms of theory, but in terms of calculations, it's much easier. Okay, we get the second derivative of R squiggly with respect to z direction. Okay, that's how we define the tangential radius of curvature, and that is simply going to be epsilon k squared times the exponential term. Hey, we got all the ingredients. We got all 3 ingredients to calculate our pressure distribution. Okay, let's plug these values inside. Okay, what do we get? Well, we just said here that P is gamma times minus 1 over R0 plus 1 over R1 plus 1 over R2. If you don't believe me, scroll up and see here, right? You see here, it's from our equation with normal stress balance on the free surface. We got this equation. We just have to plug in R0, R1, and R2. Therefore, P will become gamma times minus 1 over R0 plus this blue term and the red term. You see, oh, yay, this R0 term cancels out. We just have to organize the other terms, and if we organize the other terms, you notice that they both contain the exponential omega t plus ikz, right? They also contain epsilon. So it's going to be minus epsilon gamma over r squared times 1 minus k squared r0 squared times the exponential term. That's our pressure. Okay, we got our equation for our pressure. That's cool. So what else are we gonna find out? Well, if you just remember, why did we just calculate this when we already know the pressure? Wait, we do? Well, this is actually our second pressure, right? Second pressure. Our first pressure came from this equation a long time ago here, right? With a Bessel function with the zero guy here, right? I0kr, okay? And as I said, pressure is not just PR, but PR times the exponential term. So this is our pressure. We already solved the pressure. Why are we solving the pressure again using the boundary condition? Well, the obvious fact is that these two pressures, they are not different. They are the same pressure, but only expressed in different terms. And when the good thing about knowing a certain value in terms of different terms is that we can equate those values in order to learn what we do not know. It's like a bridge. This pressure is a bridge that connects these equations, these complicated equations together. And there we can derive what we call a relationship between these unknown values. Okay, so let's go ahead and equate pressure number 1 and pressure number 2 to find out the science behind the Rayleigh-Plateau instability, the most exciting part of this analysis. Okay, let's equate these two guys. They're the same, yay! And from our first pressure equation, another important reason why we actually applied the boundary conditions is because we wanted to find out the C, which is a constant. And the first pressure equation is useless if we do not useless, but kind of useless if you don't know what the C is. And the C, we just got it from our first boundary, we didn't actually get it from, okay. We got it from the kinematic condition, right? Not the second, not normal stress condition, but our kinematic boundary condition on the free surface. So, hey, there's a reason why we did this boundary conditions. It's useful. We got the C now. This was from our first boundary condition, and this is from our second boundary condition. Okay, good job, boundary condition. Now, let's equate the two P's. Okay, let's equate the two P's. First P is this guy, second P is this guy. And we are gonna plug in our C, our constant here, from our first boundary condition into the first P now. Yay, it's not a constant anymore, it's determined. Okay, what else can we get rid of? We can get rid of this guy. We can get rid of this guy here. We can also get rid of this guy. Finally, we can get rid of this guy, which has been tagging along for too long, more long than I would have liked. And we have these, there's nothing more to get rid of now, okay? So let's, what should we do? Let's organize this in terms of our omega squared because that's what we want to know. Okay, if we put everything else to the right hand side, we will get a value using something called this. Okay, omega squared is this difficult looking guy, and I won't read this, but you can see that it is determined by both the Bessel functions with n equaling 0 and n equaling 1. It is proportional to surface tension and inversely proportional to rho, and you can see that there is a k here and an r0 here, and everything is multiplied by 1 minus k r0. So you can infer that there is a KR0 here, there is a KR0 here, and there is a KR0 here. So KR0 is going to be a very important term when we are trying to write a function or graph or trying to find the relationship between omega and k. So everything is going to be expressed in terms of k times r0 from now on. Another important fact is that unstable modes are only going to be possible when kr0 is smaller than 1. So we will not consider cases when kr0 is larger than 1. Okay? That's just from mathematics, from unstable modes, differential equations. Yeah. Okay. And another important fact is that we have a function written which is a relationship between omega and k. And in science, in general, we say that any relationship between omega and k is called a dispersion relation. It doesn't really have to be fluid mechanics, but it could be from solid state physics or whatnot. Omega and k, if you're dealing with waves, for example, omega and k, it's gonna be what we call a dispersion relation. That's a nice fact to remember. So this is our dispersion relationship. So it kind of, you have to actually use a computer to draw this graph, but like I kind of drew this graph with my hand. It's not completely accurate, but it kind of looks like this if you tell your computer to draw this. So if you get a relationship between omega and in this case kr0, r0 is just a constant, so we can see that this is a valid dispersion relationship. And you can also like use like the y direction as a like omega and its relationship with the critical time as well. Anyway, if you solve this numerically using the Bessel functions, you will get that the maximum omega occurs when kr0 is 0.697. This is a very important number to remember. So when kr0 is 0.697 omega, so I just plugged in kr0, this guy, like I said that it was 0.697, right? 0.697. And if you calculate this, plugging it in here, here, and here, so you will get a certain value for omega squared, right? Or omega. And that's how we just calculate this guy, which is 0.3433 times the square root of a gamma over rho r cube. And you will remember that this has something to do with our critical time. Okay, if you look at the previous videos. Okay, so as I said, the maximum omega occurs at kr0 equals 0.697, and here we know also that our lambda max can be expressed as 2 pi over k, which is 2 pi over k, which is equal to this guy, 9.01. 9.01, am I correct? 9.01 or sometimes 9.02 R0. And we also know that the critical time and the critical length can be determined in our case. So how are we going to determine our critical time? We just said from our very first video that it is determined by saying that it is 1 over omega. So therefore we can just take this omega guy here, we take the 1 over omega here. So that's how we end up with our value, which is going to be 2.91 times this rho r cubed over gamma square. Also, the critical length is just going to be quite similar, but it's our 2.91 times the the jet speed, times this square root value, because it's time multiplied by speed. Okay, we did a lot of analysis today, and the last one I want to talk about is a certain case when we have a vertical water jet impinging a horizontal reservoir of water. So if this jet is gonna impact or impinge on this system, there's gonna be a field of standing waves, okay? Standing waves. So they are going to be excited on the base of our jet. And the wavelength here will be determined by the requirement that the wave speed corresponds to the local jet speed. And the local jet speed here is, as I just wrote down, u, which is minus omega over k. But we know the dispersion relation, so we can simply write that u squared is also omega squared over k squared, right? Therefore, if we know all the other values, we just solve the equation for omega, and we just set that omega is this guy here, right? This guy, omega squared. So if you do omega squared over k squared, which is u squared, or the square of the local jet speed, it's gonna be like this. So this is one example of how you can determine the values of a certain system using our dispersion relation, provided that the jet speed, like u, is known. For example, you can solve this equation to deduce the wavelength of the waves, which will be traveling at this jet speed. And yeah, for we can also derive like similar equations for jets falling from nozzles and many other practical engine